We now turn to tonight's lecture on chance versus necessity in mineral evolution, and it's my pleasure to introduce tonight's speaker, Robert Hazen. Bob is Senior Staff Scientist in the Geophysical Laboratory at the Carnegie Institution and Robinson Professor of Earth Science at George Mason University. He also is the Executive Director of the Deep Carbon Observatory, a 10-year project to study the chemical and biological roles of carbon in the Earth's interior. Bob's research focuses on the role of minerals in the origin of life, the coevolution of the geosphere and the biosphere, and the development of complex systems. He is an author on more than 400 scientific articles and 25 books, including Genesis, The Scientific Quest for Life's Origin, and The Story of Earth. He is a former president of the Mineralogical Society of America, and he is active in presenting science to non-scientists through writing, radio, TV, public lectures, and video courses. He earned a BS and an SM in geology at MIT and a PhD in earth science at Harvard University. In addition to his earthly pursuits, so to speak, fairly recently he retired from 40 years as a professional symphonic trumpeter. His talk tonight is on chance versus necessity in mineral evolution, a new approach to an ancient subject. Please hold questions to the end and join me in welcoming Bob to the podium. Doesn't want to, okay. Now let's see if we can get this to come up. Hello.
Wonderful.
Sorry.
Thank you, Larry, and thank you all for being here this evening. We live on a planet of breathtaking beauty. Seen from the proximity of our moon, we see the swirling white clouds above the oceans. We know it's a planet that's vibrant with rich and diverse life. And it's only logical to ask, are we alone in the cosmos? Is Earth somehow special or unique? And what exactly do we mean when we talk about Earth-like planets? Tonight, I want to address this from the perspective of an earth scientist, and particularly a mineralogist studying the natural materials at Earth's surface. And I want to do it in 3 steps. First, I want to ask a question about how minerals have changed through Earth's deep time, something we call mineral evolution. And then examine a rather new direction in mineral research called mineral ecology, where we're thinking about the diversity and the distribution of minerals on an Earth-like planet, and what that's telling us about Earth's present state and its history. And finally, explore this question of the coevolution of the geosphere and the biosphere, and connect this with that profound mystery of the origins of life. Throughout, I'm going to be thinking about this question of chance versus necessity. To what extent are the things we see on Earth today deterministic, inevitable, part of any Earth-like planet? And to what extent are some things frozen accidents? And one of the conclusions I'm going to come to is that this is a false dichotomy. Speaking of chance versus necessity is inherently flawed because what we find in the natural world are a continuum of things that are very likely, very unlikely, and everything in between. And I'll show you quantitatively how using mineralogy we can come to that conclusion. So let me begin by talking about mineral evolution, a rather new idea introduced 10 years ago in which we were thinking about how Earth's near-surface mineralogy changes through time. And this includes how many different mineral species are there. It includes the things about the relative abundances of those minerals in the near-surface environment, the compositions, not just the major elements, but the trace and the minor elements, the isotopes that are part of mineralogy. They change through time. And even something as a mineral collector from the time I was this big, the sizes and shapes, the colors of minerals, they also change through time. And recognizing these changes as a mirror of the dynamic evolution of our planet is a really profound and new way of thinking about mineralogy. Now, We focus exclusively on the near-surface environment, the upper 3 kilometers, and for very logical reasons. That's where we can sample most easily. It's where we're going to see when we look at other planets and moons. And indeed, comparing Earth with other worlds is a very important part of this whole effort. And it's also the part that interacts directly with biology. And you're going to see tonight that biology plays an incredibly important and previously unrecognized role in Earth's near-surface mineralogy. I have to make a comment about evolution. Some biologists have complained that we talk about minerals evolving. But in fact, all kinds of complex systems evolve. And what we mean is the basic idea of change through time. It's used all the time in science. The Evolution of the Igneous Rocks was a book published 100 years ago and reflects this kind of thinking. It also implies a complexification, a diversification, an increase in patternings. And so a more interesting system, and complex systems tend to become more patterned through time. There also is the implication of congruency, the idea that each step within this framework follows logically from the steps that came before. So there's a sequence. However, it's not Darwinian evolution. There's not a progression. A quartz crystal is a quartz crystal is a quartz crystal. So erase this from your mind. Different complex systems have different characteristics, and that's for sure as well. That's one of the interesting things about studying these. Okay, so the key idea of mineral evolution is that new mineral species arise through a combination of physical, chemical, and biological processes on Earth. And to give you a sense of how this is new, how this is different from the way people thought before about 8 or 10 years ago, here's a question which may seem very logical to you to ask. Any scientist would ask, what's the first? What's the earliest? What's the origin? And yet, try as you may, look back through the hundreds of years, the centuries of mineralogical research, and you will never find this question. It simply had never been asked. What is the first mineral in the cosmos, in the history of the cosmos? Now, a mineral is defined as a crystalline substance, so it has a crystal structure, and it has a fixed composition. So any combination of crystal structure and composition that's unique is a mineral species. Today, by the way, there are about 5,000 recognized and approved mineral species. But what was the first one? What was the first crystal? Oh, I hear some good answers here. So what's the first crystal in the cosmos? Now you think about it, it wouldn't have been at the Big Bang. The Big Bang things were much too hot. There were no condensed phases, certainly no crystals. And furthermore, the first elements formed in the Big Bang were primarily hydrogen and helium, gases that simply don't form crystals. And so you say, well, okay, you wouldn't have had crystals then. But then what happens? You form stars. When you form stars, you go through the process of nucleosynthesis, especially the large stars, which start making heavier and heavier elements. From helium, you get carbon and oxygen and nitrogen and magnesium and silicon, all the way up to iron, and then you have a large enough star, it collapses, it explodes. You litter the cosmos with all the other chemical elements. Suddenly, you have an opportunity to make crystals. And we think that the very first crystals were from one of the most abundant elements, the ones that were enriched in the outer envelopes of those stars, and as the stars expanded, the energetic stars and the winds blew these atoms out. You had a sufficient concentration, but cool enough temperatures to crystallize in these supernovas, maybe also in energetic stars that had very active solar winds, the very first mineral. And the reason is because carbon is an abundant element. Carbon atoms could find each other, and it has the highest temperature of condensation, about 4,400 degrees Kelvin. Now, as you cooled another 400 degrees, the second mineral comes along, and that's graphite. It's the more stable form of pure carbon, and it forms at about 4,000 Kelvin. And then there's a sequence of minerals, about a dozen in all. It's what we call the minerals. For the ancient city in Mesopotamia, which is the origin, the founding. We talk about text. We talk about, so this idea of the minerals, the very, very first, the starting point of all planets, of all the materials that we understand. This is where they came from. And these dozen or so phases represent just 10 different chemical elements, all very abundant in materials. And I guess the core question of mineral evolution then can be phrased, how do you go from 12 mineral species using only 10 different chemical elements to what we see today, which is more than 5,000 minerals using 72 different chemical elements? It's that progression that we're trying to understand. And we can understand it as a series of Good heavens. Well, I can tell you about this because it's really, you imagine early in the cosmos, you have the nebula of dust and gas surrounding the proto-sun, the hydrogen and helium mostly concentrating 99% of the mass into that central growing sun. And then the planets beginning to form ever so slowly. But the very first steps of that, when the solar body begins to ignite, when the radiation sweeps out from the sun, you heat that dust and gas, and you form the very first droplets called chondrules. Those droplets then condense new minerals, about 60 minerals in all. We can keep going from here. Let's see where we end up. This is like a good review. There we go. There's the nebula. There's the proto-sun up in the corner. There's things condensing. And the very first stage in mineral evolution then are the 60 minerals that are still found to this day in the most primitive meteorites, collections of tiny droplets of fused materials condensed into what are called chondrite meteorites. Then, of course, the chondrites themselves begin to collect into larger and larger objects, things the size of this room, things the size of Washington, D.C., things the size of the inside of the Beltway, 100 kilometers, 200 kilometers. And when you start getting to those sizes, then you start getting interior melting. You start separating your core from the mantle. You have many, many other minerals, and that's stage 2 of mineral evolution, about 250 minerals that are still found in all the meteorites that fall to Earth today. That's the next step. So we've gone from 12 to 60. To 250. These are the building blocks of the planets. When you start forming planets, you get more differentiation. You get more interaction between the near surface and the deep environments. New minerals start forming. And in the case where you have a very dry world of this source, like the moon or Mercury, we estimate we might be able to get up to about 300 mineral species maximum. And that's it. I don't think you're going to find more mineral species than that on our moon, for example. But if you have a wet world like Mars, like Earth, you then form other sorts of things. You form hydroxides and clay minerals. You can form evaporite minerals. You can form ices if it gets cold enough at the polar regions. And so we start seeing perhaps 420 mineral species that we can identify that would occur in this sort of environment. We think this may be the end point for Mars, unless Mars has some tricks up its sleeve that we haven't found yet. This is probably the mineral richness that we'll see on that planet. Earth has other tricks. Because Earth is larger, Earth has a lot of water that's circulating. It has internal heat. You can form a crust of basalt, heated from below. The basalt, when it's wet, melts partially and forms something called granite. The granite contains all sorts of rare concentrated elements that can form hundreds of new mineral species. We get up to 1,000 minerals with granites. And then another trick is plate tectonics. Plate tectonics, the incredibly vast scale of reworking the crust and mantle. So what you see here, thank you. What you see here are processes because of volcanism, because of forming massive sulfide deposits with all sorts of new minerals. We can get up to perhaps 1,500 mineral species. 1,500 mineral species on Earth as a result of chemical and physical processes alone. But try as we will, that's it. You seem not to be able to get beyond 1,500. And yet Earth today has over 5,000 known mineral species. So the question is, how do you get from 1,500 to 5,000? The answer is life. An astonishing revelation that 10 years ago would have been heresy in mineralogy and now is accepted as the key to understanding how our planet has evolved. Okay, here's an interesting point. Almost all the theories for the origin of life invoke the use of some kind of minerals as templates, as synthesis catalysts, as ways of protecting molecules, as ways of constructing and self-organizing molecular systems. But what we find now is that the further evolution of minerals requires the origin of life. So the origin of life requires minerals, the origin of minerals requires life, hence the coevolution of the geosphere and biosphere. Fast forward, stage 7 is the big game changer. This is when life finally learns how to make oxygen. And as the oxygen enters the atmosphere, it changes the near surface environment in dramatic ways, leading to thousands of new mineral species, just simply through oxidative weathering. So that's one big step. And when we think about this proposal, this hypothesis that fully 2/3 of the minerals on Earth are biologically mediated. That requires a little bit of proof or a little bit of explanation. So here's our idea, the idea that has been around for a long time, Earth's history, 4 billion years going back in time, and the change in Earth's oxygenation in the atmosphere. For a long period of time, it was extremely low. People don't say exactly how low, but very low. Then there's a period when it gradually rose, and finally, at the very end, the last 500 million years or so, it rises to more or less modern levels of 20% of atmospheric concentration. Now, this means that many new minerals wouldn't have appeared until you had oxygen available to cause the weathering. Okay, why do we say this? First of all, we look at minerals that contain oxygen-sensitive elements, including all these metals and also nonmetals. And more than half of all known minerals contain these elements. So they're all indicators, they're markers for Earth's state of oxygenation. And here's the kicker. In Earth's near-surface environment, there's a huge amount of iron. Iron is the most abundant of these redox-sensitive elements. It can occur in the divalent state, +2, or the trivalent state, +3. For a long period in Earth's history, the oceans, the near-surface environment, had a huge amount of the divalent iron, the more reduced one. Now, on the vertical scale of a graph like this is something that represents the activity of oxygen in that near-surface environment. So it tells you how much oxygen was available to react with its surroundings. And for a long period of time, we were buffered. We were right along this line where two minerals, hematite and magnetite, coexisted. They formed great banded iron formations. And it turns out that the numerical value is 10 to the minus 72. Just keep that value in mind, 10 to the minus 72. That's the level, the activity of oxygen. And at that sort of level, you could titrate out the iron and maintain a constant oxygen fugacity, oxygen redox state. So what you find is you go various places in the world where there are rocks that are 2.5 to 2.7 billion years old, and there are huge amounts of iron formation. The world's largest iron mines come from this age. This is from Western Australia, where until recently, when China had stopped as much shipping, 100 million tons a year were being shipped out of here. This is an incredible place. So 10 to the minus 72, what minerals would form? An iron carbonate, which is very well known from these early rocks, is siderite, FeCO3. And siderite forms in this one little wedge. In other words, you have to be sort of below and to the left of these green lines. And that means you have to have a log FO2 of less than 10 to the minus 68. Okay, 10 to the minus 68, that's close to 10 to the minus 72. It's a completely reasonable number. And we know that siderite formed at these times. But what wouldn't form? Played the same game with two of my favorite minerals, azurite and malachite. These are copper carbonates. And you see the fields for azurite and malachite, and you have to be in the upper left-hand corner here. That means you have to be greater than 10 to the minus 43. That's almost 30 log units in oxygen activity, higher than the buffer at the time. You simply can't form azurite and malachite on early Earth. It's not until organisms learn to produce oxygen, change the redox state of the near-surface environment, and then you could form these beautiful minerals. Almost all the beautiful copper minerals you'd see if you go to a museum. 90% of the uranium minerals, these beautifully colored minerals that you'll find, again, in any museum that you go to. The minerals of nickel, and almost all the minerals of cobalt, and element after element this is true for. So, thousands of minerals that only formed after life produced an oxygen-rich environment. So here we see that minerals played these key roles in life's origin, but the same token, life played key roles in the origins of minerals. That's the coevolution. I'll tell you about one other stage, the last stage, the most recent stage, the last 400 million years, 450 million years or so. And interestingly, when you talk about an Earth-like planet, what most of us think of as an Earth-like planet, Earth has only looked like that for the last 10% of its history. And that's when life came on land and we became a green planet. And there are hundreds of new species that result from this. Partly they're clays, they're biominerals, they're various kinds of materials that form shells and teeth and bones. There also are some amazing changes, and we see when we talk about this coevolution of Earth and life I'd like to tell you about two speculative ideas that are just now emerging that I think are remarkable for how they tell us the new way of thinking about the Earth. Never before is this true. So, about 200 million years ago, life learned to do something that had never happened before. In the middle of the deep ocean, plankton could begin to make their own calcium carbonate shells. Prior to this time, the only place that life made calcium carbonate was in the reefs right along the shoreline. But now you could make these objects in the middle of the deep ocean, pulling the CO2 right out of the air, making shells, and when the shells died, they sank to the ocean floor. So for the first time in the deep ocean, there were large accumulations of calcium carbonate shells. At the same time, we have a situation with subduction. This is plate tectonics, where huge amounts of ocean crust are taken into subduction zones and brought down deep into Earth's interior. 3 billion years ago, when that happened, it was hot enough that the calcium carbonate decomposed. The CO2 came back to the surface. And you see that with the temperature scale on the horizontal line. In orange is what happened 3 billion years ago. But things have gotten cooler. This geotherm has moved to the left. And now, when calcium carbonate is subducted, most of it will just keep on going all the way down to the lower mantle and be sequestered. Well, what does this mean? Is it possible that we've now entered an area in Earth's history that for the first time, the net carbon budget at the surface is negative? We're burying more carbon and more of it's getting down into the mantle? If you do a back-of-the-envelope calculation, one result is that within 300 to 400 million years, Earth's surface will be stripped of its carbon. What does that mean for life? Well, we don't have to worry about it, but it's certainly an interesting idea. The idea that somehow life, because of the formation of these planktonic calcifiers combined with plate tectonics, is actually changing the entire global carbon cycle in a fundamental way. So that's a global scale process that life may be conducting. And let me tell you about another one that's sort of similarly wild. The first plants with roots introduced about 400 million years ago. And they're little tiny things, just a centimeter or so in fossils that you can find in Scotland. But within a few tens of millions of years, the roots got deeper, the soils got deeper, the plants grew taller, and then the roots got deeper, and the soils got deeper and deeper and deeper. Well, as roots began to make more and more soils, and you start getting systems like this, which you can see today, one of the consequences is the formation of vast amounts of clay minerals that had never been formed before. And these clay minerals, of course, then form in coastal areas. They, for the first time, armor rivers. There are all kinds of subsurface communities, ecosystems forming. Fungi began to be part of the story and were more efficient at breaking down rocks. Microbes came into the picture. And so we went from a land that looked like this to a land that looked like this, and rich soils and clays that then got washed into the ocean. Well, think about that. You've got a system where you have subduction zones going underneath the continent. You've got now land masses that are producing vast quantities of clays. The clays actually can act as a lubricant for plate tectonics. And so one of the speculations is the rate of plate tectonics has been accelerating. And the reason it's accelerating is because of life producing clay minerals. So I don't know if it's true. It's something that we have to think about, but this idea of the connection on global scales of life and rocks is a profound and new thing, and it stems out of the kinds of thinking that led to mineral evolution. So we have to think about our globe in a new way. The conclusion of mineral evolution is Earth has transformed repeatedly and in dramatic ways over the last 4.5 billion years, and we can study those changes by studying the minerals. Life and minerals co-evolve. Okay, so I've just described mineral evolution, and we're thinking of minerals now as a complex evolving system. And like all complex evolving systems, there's certain characteristics. There's diversification. There's also extinction events. We have congruency, each step following logically. We have these twin ideas of punctuation, rapid change, like in the Great Oxidation Event, but also periods of perhaps 1 billion years when very little new happens, stasis. And that's true of all these complex evolving systems. We have feedbacks. We have selection rules. And we have the opportunity of thinking about these systems in terms of this dichotomy of chance versus necessity, frozen accidents versus deterministic aspects of the system. This is true of any kind of complex systems. We can talk about nucleosynthesis in stars. We can talk about organic molecules being synthesized before the origin of life. Talk about the evolution of complex systems like life itself, and also material culture. We can talk about language. We can talk about Broadway musicals. Anything you want to talk about where there's a chronology and evolution fits these different criteria. But I want to focus now. Think about Earth. To extent, think about life. And this question of chance versus necessity. Can we, in fact, get a quantitative understanding of how chance versus necessity plays a role in an evolving system? And it turns out with mineralogy we can do this. Now, this is an old set of debates. Perhaps most famously, Jacques Monod has his book, Chance versus Necessity, and he has this rather pessimistic, very French kind of approach. The universe is not pregnant with life, nor the biosphere with man. Man at last knows that he is alone in the unfeeling immensity of the universe out of which he emerged only by chance. Okay, 6 years later, this was countered by Ernest Chauvinel's anti-chance. The origin of life and evolution were necessary because of conditions on Earth and the existing properties of the elements. Okay, that's a interesting debate. There's extremes there, and both of these authors were more nuanced than that, but it certainly seems like a dichotomy is being set up. So let's think about the origin of life. First of all, basic assumptions: the origin of life is carbon-based, standard organic chemistry. Basically, you have rocks, you have water, you have atmosphere as the raw materials to build with, and that the origin of life requires a sequence of chemical reactions. That's the key here, chemical reactions of increasing complexity. So we're going to think about what, in fact, in terms of the sequence of chemical reactions is deterministic and what is chance. So chemical reactions in life, they involve rearrangements of atoms and their electrons. Three very common ones that you find in nature and all life uses include things like rusting, cooking, and acid. And these are examples of oxidation-reduction reactions where you're moving electrons around. In this case, polymerization, depolymerization reactions, and also hydration, dehydration reactions where you're moving small molecules, particularly water molecules, around. And in this case, you're moving protons around in acid-base reactions. That's what life does. Life does these chemical reactions all the time. So the question is then, what are the chance versus necessity in terms of chemical reactions, and how can we possibly know? Well, I'm going to claim that Earth's chemical reactions display a range of probabilities. And what I'm going to do is use minerals as an example, because every mineral species, every one of those 5,000 mineral species represents a chemical reaction. I'm going to show you how we can determine the probabilities that those reactions occur. So this is mineral ecology. This is last year's sort of new idea, and it's really exciting. My team and I have been thinking about using diversity and distribution relationships of minerals to understand probabilities. Here's what we do. We have huge databases of minerals. We have databases that list all 5,000 known mineral species. We have databases that list thousands, 125,000 or so mineral localities, and there are over 650,000 pairs of a mineral species at a locality. That's called a species locality data point. So each one of these data, it's like there's a particular outcrop in Rock Creek Park that has quartz. So that's quartz from that outcrop. That's one data point. And we have these huge databases. And what we can do is look for quantitative relationships between diversity and distribution. It turns out, make a long story short, we realize that the distribution of minerals across Earth's surface is almost exactly mathematically analogous to the distribution of words in a book. Specifically, there are a few words that are very common and a lot of words that aren't. We can also see a similar relationship in ecosystems. So look at a redwood forest. Almost all the biomass in a redwood forest is redwood trees. But the diversity of these little rare things that are at the base of the trees, the little insects, the little worms, the ferns, and some of the other things. And so by studying all the things in an ecosystem, the rare things and the common things, you can get a sense of the diversity and also what's missing from your sample. The mathematics we use, though, is specifically from the manuscript world. Lexical statistics which thanks to the NSA are now a highly refined science, mathematical science, because of course they're trying to figure out who wrote a particular email and if a particular manuscript is attributable to one author or another. So most words are common. The rare words define the diversity in the authorship. And furthermore, if you have a complete list of all the words in their distribution, you can, for example, predict the vocabulary of that particular author, the total vocabulary, even though many of the words don't appear. Same thing for Earth. We can predict the total mineral vocabulary for Earth, even though many of those minerals have not yet been found. What we find is that a few mineral species dominate. 99% of Earth's crustal volume is only 100 mineral species. But there are thousands and thousands of species that are rare, and it's those rare ones that follow this particular statistical approach, the large number of rare event distributions. What this means is basically, if you do accumulation, these are the number of minerals known from exactly one locality, exactly two localities, three, and the cumulative percentage, more than half of all minerals on Earth are known from 5 or fewer localities. And most of those localities represent single microscopic crystals. So we're talking about very, very tiny, tiny amounts of these rare things. This is what the distribution function looks like. Exactly one locality, more than 1,000 mineral species on the vertical scale are known from exactly one locality. Another 800 or so are known from exactly two localities. Another 400 or so from exactly three localities. And you basically have a distribution in which most minerals are rare, and you have this very characteristic tailing. This is an LNRE distribution fit to a GIGP type of function. If you're interested, I can give you the papers. But the long story short, you can use this in this model to make all sorts of predictions. In particular, we can do what in biology is known as an accumulation curve. Imagine going to a forest, and you come to the first tree, and you mark down the species of that tree. And then you come to the second tree, and you mark down that species. And for a while, you're keeping adding new species, 10, 20, 30, 40 species of trees. And then you may have to look for another 20 or 30 trees before you find a new species. And they're getting less and less common. And you have an accumulation curve that asymptotically approaches what you estimate to be the total number of trees, the diversity in the forest. You can do the same thing with genomes. So if you have a microbial population, you can sample more and more tagged sequences. And as you do that, you get an asymptotic approach to what you assume is the total diversity, even though you're not seeing every one of those species. Well, we can do the same thing. Here's the number of these mineral locality counts. As I said, we're up to about 650,000 right now. On the vertical scale is the number of approved mineral species. And when you first start looking, you find things raising very, very rapidly. The number of new species increases. But it starts tapering off. There's where we are as of February 2015. About 650,000 pairs, about 5,000 species or so. And it extrapolates out that there's another 1,500 mineral species that have not yet been found but exist on Earth and could be found using the same techniques that we've been using all along. So we're making these predictions. So we predict there's about 1,500 mineral species. What are they? And we can use the same kind of statistical methods by taking subsets of all the minerals. For example, here's the statistics for just the minerals that contain carbon, the element carbon. Most of these are what are called carbonate minerals. 82,922 different locality species data, 403 species, and we can do the accumulation curve, and we see that a similar kind of accumulation curve. We predict that there are 145 additional carbon minerals. We've just started something we're calling the Carbon Mineral Challenge, which is an international competition to find some of those minerals. We predicted what they are. We've predicted where you go to find them. And this will be a new test because in mineralogy, never in history have we had the ability to predict and then go out and test those predictions in this way. This is a lot of fun. This will be the next 4 years. Keep watching the news. I think the first discovery is already about to be announced after just a couple of months. So we're pretty excited about that. Anyway, another thing you can do with these statistical methods is predict the probability of any one species being found. Here we have ranked all 6,400 some mineral species with the vertical scale's probability. And what you find is that there's a large number of minerals, more than half of them, which are extremely likely to be found if we replayed the tape of Earth a second time. Very likely. There are another group of species that have a greater than 50% probability, and another group, a fairly sizable one, where it's less than 50-50 to find them if you replayed the tape and discovered the same minerals all over again. So you can look at this and say there's some minerals that are a necessity, almost 100% probability, and there's some minerals that are frozen accidents, less than 10% probability, and those are what I call chance. But look at that huge number in between. Probabilities that aren't 100%, they're not less than 10%, there's someplace in between. There's a continuum. And every one of these 6,400 points represents a chemical reaction occurring on Earth. Some chemical reactions are extremely likely. Some chemical reactions are extremely unlikely. Some are 50-50. There's not chance versus necessity, it's a set of probabilities. And that's the way we need to think about origin of life. Okay, so each mineral species represents one of these chemical reactions, and we say something about that. Now, the third part of this talk is going to be a back-of-the-envelope calculation to say how likely is it on Earth that we're going to have these chemical reactions. Well, if there's a sequence of chemical reactions, some are more likely than others, then we really have a problem, and especially because we know it's a sequence and that there may be many different pathways to a viable living system. So we really can't say in detail what any pathway is going to be in terms of probability. What we can say, though, is that Earth gives us an incredible opportunity to try lots of combinations. So what I want to ask after this point, chance versus necessity is a false dichotomy, is let's think about a planet like Earth and how it samples all of this composition space, how it samples the possible reactions. So I want to claim the chemical reactions that are extremely impossible at a laboratory scale could be absolutely deterministic at the scale of a planet over billions of years. And here's how we're going to do this. We're going to do a back-of-the-envelope calculation. How many chemical reactions can occur in a planet? There's the envelope. There's the calculation I did when I first did this. And basically, you have to know four things to do this calculation. First thing is, how long does it take for a reaction to take place on a mineral surface? Now, the idea here is that reactions, chemical reactions, are going to happen most effectively on a surface, at an interface. It could be the surface of the ocean. It could be a tidal pond that's evaporating. It could be a mineral surface. But you need a surface. That's where molecules concentrate and they react very quickly. And it's going to be a relatively rapid thing. You also need to know what's the surface area that you need for each one of these reactions. So think on the scale. Each chemical experiment is going to be on a tiny area on a small amount of time. And then we think about Earth as a planet. How much time does Earth have? And how much surface area does the planet have? So those are the four numbers we need, and you'll see what I mean by the back of the envelope. So how long does it take for a reaction to occur on a mineral surface? Well, there's a lot of data on this. The reaction times vary widely. It's very often less than a second. Molecules very, very quickly interact and react. I mean, sometimes it could be 1 million reactions a second. But let's just, for a very conservative answer, let's say it takes on average 10 seconds per chemical experiment on a surface. That's the first number we need to have. Second number is, what's the surface area? Well, most of these molecules are less than a few nanometers across, and the repeat distance on a crystal surface is less than a few nanometers across. So again, being fairly conservative, let's say that the total surface area you need is 100 nanometers by 100 nanometers. So, 100 nanometers square. That's 10 nanometers by 10 nanometers, or 10 to the minus 12th square centimeters. So that's the surface area for each one of these reactions that takes place every 10 seconds. All right, now let's think at a global scale. How much time does Earth have? We know that life was present 3.5 billion years ago. There are fossils in Western Australia that very clearly show that. There's some evidence that there might have been life 4 billion years ago. So if Earth is 4.5 billion years old, that's sort of, as a conservative estimate, say we had about 600 million years to get life started. Could have been 1 billion years, it could have been 100 million years, but it's something in that order. And so that's 2 times 10 to the 16th, 10 to the 16th seconds. That's the third answer. And now the fourth one is what's the surface area of Earth. This is by far the trickiest one to get a really accurate estimate because mineral surfaces are complicated. But here's how it is. The total surface area of Earth is 5 times 10 to the 18th square centimeters. That's something you can just look up in any atlas. Now, the surface area of the near-surface minerals arises because they're particles, they're sediments, sand grains, clay grains, and so forth. So the total surface area is not just 1 square centimeter, but every square centimeter has lots and lots of surface area where molecules can interact in a fluid medium. You get nanoparticles coming out of volcanoes, for example, black smokers on the seafloor, and volcanoes like this. Huge surface areas involved in these kind of ash clouds and so forth. So that's the materials we're looking at that really contributes to the amount of surface area. The most remarkable ones are the clay minerals, which dominate the near-surface environment. 2 times 10 to the 6 square centimeters per cubic centimeter. So what exactly does that mean? Here's a sugar cube. That's a cubic centimeter or so. And if you have a cubic centimeter of clay, the total amount of surface area represented by that is about a tennis court. So just think, for every square centimeter of Earth's surface, you have to think about how much depth is there, how many clays, and how much area does that represent. Now, I'm going to be very conservative here and estimate that we're talking about an average of 1 meter of soil for every square centimeter on Earth's surface. So that's, about this much, a tennis court for every cubic centimeter, and you can start multiplying that out. And what you find is that for every square centimeter of Earth's surface area, you just multiply it out, 100 cubic centimeters per square centimeter, and it turns out it's a lot of clay minerals. 500,000 cubic kilometers of clay minerals. And if you look at the total amount of surface area, that's a tennis court for every cubic centimeter, it's 10 to the 27th square centimeters of surface area. All right, a lot of numbers being thrown out, but basically it just means that Earth had this amazing amount of surface area to play with. It had a lot of time to play with, and each experiment only takes place on a tiny, tiny surface area over very short time periods. So let's do the math. You have to multiply the surface area of Earth times the time available, divided by the surface area of an individual experiment times the time for an individual experiment. Those are the 4 numbers we just came up with. And the result is 2 times 10 to the 54th chemical experiments for an Earth-like planet. That's a big number. So the point is 2 trillion, quadrillion chemical reactions, molecular reactions occurring at Earth's surface, some of which are going to be extremely likely, some of which are going to be very unlikely. But even if they're extremely unlikely and something you'll never, ever run across in a laboratory experiment in the time frame of a graduate student doing a PhD, Earth can do it because it has this time. So things that are highly improbable on the scale of an origin of life scientist's career may be absolutely deterministic on the scale of an Earth-like planet. All right, that's the thing. So here's some of my graduate students and postdocs. They won't be able to get this done, but Earth can do it. Okay, Mars can do it. That's the bottom line. So what do we do? This seems like a dilemma, doesn't it? Because if the origin of life is deterministic, but there's not a prayer that we can figure it out just by doing a whole bunch of experiments, because you can't do 10 to the 54th experiments, you use chemical and physical intuition. That's what scientists always do. You look backwards, you look at modern biology and see what chemical reactions life uses and then try to mimic those particular reactions in a laboratory environment. Use new combinatoric approaches. There are all sorts of ways that you can do lots and lots of different chemical experiments simultaneously. And also some of these in silico. You use a computer to run through possible reactions as we understand more and more about reaction kinetics. And we hire a lot more great students because they're the ones who are going to do the work and they're going to have the next great ideas. So here's some of my colleagues that I've had the pleasure of working with over the last few years, all involved in one way or another with this origin of life research. And so that's the next generation. That's the future. That's how we're going to solve these problems. So I've got 3 main conclusions. Life's origin can be understood as a sequence of chemical reactions, concerted, And they all take place in a geochemically complex environment with lots of different minerals, with fluxes, with cycles, with all sorts of ways of mixing things up and changing the broth. You can think of the origin of life in terms of chance versus necessity, but that's a false dichotomy because there are things that are more probable and there are things that are less probable. And until we start understanding chemical reactions as falling in this spectrum of possibilities, we're going to miss this real question. Are we alone in the universe? Well, that falls very much into thinking about these questions. And then events that are improbable on the scale of the kinds of laboratory research that my team conducts may then nevertheless be absolutely inevitable when you look at the scale of planet Earth. I don't know if we're alone in the universe. As a person who's staked my career on studying origin of life, I guess I've decided it must be a cosmic imperative in one sense or another. It sure is fun trying to find out, and I think this new insight that understanding the mineral realm as a key to understanding the living realm and the connections between them is going to drive my science and be a lot of fun for a long time, I hope. And with that, I thank you very much for your attention and hope that we can have some questions.
So we have time for questions. There are 3 people with microphones running around. If you'll raise your hand and keep it up and get their attention, they will bring the microphone to you. And when you get the microphone, we'd appreciate it if you would stand up and tell us your name and whether you're a member of the society or you're not. The microphone will come to you. So just keep your hand in the air. Bring him the microphone.
I noticed that during your speech or presentation that you talked about reactions happening on the surface of minerals. Could you please comment on how that is affected by the composition of the atmosphere? In other words, was it like an oxidizing environment or a reducing environment with methane and ammonia, or did it have oxygen? Thank you.
Thank you. Yeah, so the question about the composition of the atmosphere, I guess for my group, we're primarily interested in chemical reactions that would have occurred on the floor of the ocean as very reduced material from Earth's mantle came up through volcanoes and hit what was certainly not an oxygenated, but it was a more oxidizing environment in the near surface. And it's this redox contrast between the very reduced mantle phases, what are called ultramafic rocks, and ocean water, forming reactions, for example, called serpentinization, which would have occurred and produced a lot of energy at the same time, even in the absence of oxygen in the atmosphere. I think that if you're talking about a near-surface environment, then the energy source is not a redox source, but it's more like the ultraviolet radiation. It's the photons that are coming in. So you can imagine many near-Earth surface environments where there's lots of energy, but it's certainly, you're absolutely correct that you can't rely on the kind of redox chemistry that we see at Earth's surface today that provides surface life with such a robust source of energy in conjunction with both photons and electrons.
Timothy Thomas, I'm a member of the Society. I'm wondering about fossil black smokers. If you look at the remains of smokers that were from millions or even billions of years ago, and you examine them closely, do you see minerals that exist there from when they were formed that are not present now? Or is that a ridiculous thought?
It's not at all ridiculous. The question of whether the mineralogy of Earth 4 billion or 3 billion years ago was dramatically different from today, I think is a very important question which we would like to be able to address. Unfortunately, many of the minerals that you'd find of that sort, now that things are more oxidized, will revert or weather or alter. Also, the deep volcanic vents, we think probably the mineralogy of those is very similar then to now because it's reduced mantle material and we don't think the mantle has changed all that much. However, near-surface environments may be very different, and there may be entire suites of minerals that occurred in near-surface, perhaps even volcanoes at the surface, where you had shallow pools and and lavas flowing down and vents of hot gases and so forth, the minerals that formed in those, often they're very ephemeral minerals. They evaporate or they wash away with the next rainstorm. They may have been quite different from the minerals we see on Earth today. So that's another variable that you have to take into account. If you're going to take minerals as being a driving force for the origin of life, you have to think about what minerals might have been present that aren't present today.
It's on.
David Rosen, a lifetime member. You put on the list tectonic motion as being a driving force for the evolution of minerals, and presumably that would also be life. But not all planets have tectonic motion, and the tectonic motion of our world is sometimes attributed to a collision that formed the Earth and the Moon. How necessary or how random is tectonic motion? I mean, in your feeling about it.
Yeah. So there's a fascinating and growing literature about what kinds of planets could have tectonics of the kind Earth sees. So we think many different planets will have what are known as vertical tectonics. You have a core mantle boundary, you have heat coming from the interior, and blebs of material rise up to the surface. That's, we think, was the dominant form of tectonics on Earth 4 billion years ago. The lateral tectonics that involves a crust forming, cooling, becoming denser, and then sinking down into the deep interior, that's something that represents a more evolved Earth, but it's extremely important in the cycling of materials that keep bringing new raw materials that ultimately provide the energy for life, the chemical energy that's needed for life. So one question is, can you have life on a planet that doesn't have plate tectonics or something of that sort? That's a big question. The other is, what's the range of planets that actually will have this kind of tectonic activity? You remember at the very beginning of the lecture, I said, what is an Earth-like planet? What do we mean when we say Earth-like? Astronomers mean something that's roughly the same size and the same density as Earth. But one can imagine a myriad of planets that have the similar size and density of Earth, but are nothing like Earth in terms of not only their chemical makeup, but their dynamics. And it's very possible that if you don't have this kind of dynamic cycling of materials, more reduced, electron-rich material from the interior coming to the surface and bringing that supply of electrons and then returning the material down. Without that dynamic cycling, perhaps it's very hard to keep the kind of robust biosphere that we have on our planet.
So I really like how you talk about the evolution of minerals in terms of speciation. And you said times of stasis and times of extinction. So is there any record of extinction events in what you've just discovered, talked about?
Extinction is very difficult to show in Earth history, but one can imagine, for example, times of hothouse Earth when a mineral ice, which is very common today. In years past, it's been much more common with glaciation, but you could also have it go extinct. There are a number of very reduced minerals. For example, there's only one mineral on Earth today which falls under a group of sulfur-bearing minerals called sulfites. More common are what are called sulfates with an SO4 group. That's the most oxidized form of sulfur. We also have sulfides, which come largely from mantle sources, and they're much more reduced. But there's this intermediate state of sulfur, an intermediate oxidation state, which is very rare on Earth today. It is used in biology, by the way, but we think maybe early in Earth history that sulfite minerals were extremely common at the surface, and they've just simply disappeared. So we wouldn't see that in the extinction record because they don't leave that kind of telltale trace, at least nothing that we've found so far. That's the kind of thing we're looking for, though.
I'm Bob Hershey, I'm a member. Are there any indications how typical Earth is of this pattern versus other places?
Boy, that's something we'd love to know. How typical is Earth? What is this goes back to the question not only of what is an Earth-like planet, but is Earth rare? People have talked about Earth being an incredibly unlikely place, that somehow the moon-forming impact and the fact that we have a single large moon plays all sorts of key roles in life. Plate tectonics plays a key role. The ratio of water, the ratio of carbon to oxygen, the ratio of magnesium to silicon, all of these variables have been invoked to say that Earth is a very special place. I was amused because in reading the minutes of last meeting, you heard about this idea of the fine-tuning of some of these constants, and if the constants varied even slightly, then the electron binding energies would be different, and we wouldn't have life, and we wouldn't be here to talk about it at PSW. Well, I think the same thing, some people have argued the same thing true for the constants that relate to our planet, the exact ratios of elements, the exact amounts of the volatile constituents that formed it, the heat budget, and the moon forming impact, as improbable as that may have been. Maybe those are all things that are critical, and otherwise we wouldn't be sitting here talking about last week's lecture on constants and time, and this week's lecture on the evolution of our planet. So these are very frontier areas of research: planetary taxonomy, planetary evolution, imagining alternative planets. One of the things that you mentioned at the beginning, that I'm part of a big project that the Sloan Foundation is funding called the Deep Carbon Observatory. And one of our ultimate ambitions is to come up with what is essentially a planetary evolution video game that allows you to set all the initial parameters and then tweak them, vary them, have impacts, have different volatile budgets, and see if the planet evolves to something that could support life or if it just dies. We don't have even the geodynamic code to do that yet, but we're working toward that. And so maybe it'll be, on your counter. Maybe it'll replace, I don't know what the hot new video game is now, but maybe everybody will be playing and building planets, and that's what we hope. That's what we want to do. So we're thinking these ways. These are great questions.
Stuart Reuter, a member. You talked about the origin of the element oxygen as if it was somehow biologically required first. Could you expound on that?
I'm not sure if I'd say oxygen was biologically required, although certainly our biology is so dependent on it. But when you think about the early evolution of all the elements in stars, just because of the nucleosynthesis process, there's certain elements that are particularly abundant. And so carbon and oxygen, to a certain extent sulfur and nitrogen, hydrogen certainly, and phosphorus a little bit rarer, but the elements that life fundamentally depends on are also elements that are abundantly available in the cosmos. I think there's probably a cause and effect there because you're going to use the raw materials that are most readily available. Life doesn't use very many rare elements, but it certainly exploits the more common ones in this way. But oxygen plays all sorts of key chemical roles. Even before oxygenic photosynthesis, all biological systems had molecules that required oxygen in various ways, in the sugars, the carbohydrates, in the amino acids, and so forth.
Many science fiction writers have talked about the possibility of a silicon-based life form. Any comment there?
As a mineralogist, there's a fundamental difference between carbon and silicon, even though they lie right above each other on the periodic table. So carbon element 6 very commonly will bond to 4 things or needs 4 electrons to complete it, to make it a happy atom. And there are infinitude ways of doing that in terms of carbon bonding to itself and then forming polymers and rings and chains and all sorts of three-dimensional structures. Silicon doesn't do that. Silicon, at least in an Earth environment, always bonds to 4 oxygen atoms in a very rigid configuration, and then that silicon with 4 oxygen configurations can link to other silicons. You can form frameworks, and you can form chains, and you can form planes. But those structures have very low and very stable energies, so they're locked into crystal forms that are not mutable. The thing that's amazing about organic chemistry is with very, very tiny energy changes, you can pull off a carbon and stick an OH group, or you can stick a CH3, or you can make a ring and you can make a chain, all these things, and they're very small changes in energy, so carbon chemistry becomes so combinatorically vast, and it's just not the same for silicon. So as a mineralogist, I would say that silicon just doesn't have the potential, even though it's on the periodic table, it visually looks like it might be the next logical thing.
Thank you.
It might have potential as the life form based on
Oh, that's interesting. Yeah, I understand what you're saying. In silico, yeah.
Carl Merrill, a member of the Society. One comment is that Martin Rees, the Astronomer Royal of England, commented that silicon-based life, that is computers, may play a later role in evolution as the artificial intelligence increases. So it would replace our carbon form, and it may be true in other parts of the universe. But my question is, years ago, Arthur C. Clarke postulated the possibility of exotic forms of life in the large gas planets. And there's a tremendous diversity there, so I wondered if you might want to comment on that.
So this gets maybe a little farther away from my comfort zone, but I see that living systems have to display some kind of combinatorial richness where there are vast numbers of possible configurations, and some of those configurations carry information and can pass the information on. When you're talking about carbon-based life forms, the combinatorial richness comes from carbon chemistry. The fact that you can line up different building blocks that are very similar that contain information like DNA or RNA. When you're talking about in silico life, you're talking about combinatorial richness of electronic states within a very ordered crystal. So it's not the atoms that are giving you the information, it's the electronic states. And when you're talking about a plasma life, you have to think of some other information carrying capacity. The common theme of all these is the combinatorial richness of a system that can carry information. But it's life on Earth that's based on atoms, and carbon is the one atom that has that combinatorial richness, as opposed to electronic structures or photons or some other combinatorial richness that might occur elsewhere in the cosmos. Does that make any sense at all, what I just said? I was saying lots of words, but I'm not sure they connected in a logical pattern. No? Okay.
Have a
Thank you.
question over here?
For that.
No, excuse me. The question's over here, please.
Judy Barrett, guest. If I heard you correctly, I think you said that half of the minerals came from 5 locations. I'm curious as to where those 5 locations are. Are they geographically centered in one area, or are they widely dispersed?
I love the English language because this is the kind of ambiguity that creeps in. What I meant is that over 2,500 mineral species, each of which is known from only 5 different localities, but the ichneus site is known from 5 localities in Russia, Kazakhstan, Bolivia, El Salvador, and Utah, and Nevadaite is known from Nevada and 5 other localities. And so they're all incredibly rare. Hazenite's known only from Mono Lake in California. So there's thousands of different localities where those rare minerals are found, but each one of those minerals is only known on Earth from 1, 2, 3, 4, or 5 places. That's what I meant. There are a few localities that are incredibly abundant. There's a copper mine in Namibia called Sumeb, which has over 700 different mineral species, which is just mind-boggling. I mean, that's like 15% of the total known mineral diversity. And that's because there's the ore body, and then it was altered once, and it was altered again, and it was altered again, and then fluids came in and altered it again, and different fluids came in and altered it again. And you have these like rinds, and each rind is a completely different set of rare minerals and exotic minerals. So there are some crazy places like that. And so there are a few places on Earth that have very high mineral diversity and a large number of rare species. But the rare species are diversified. There's one in Carroll County, Maryland, for example, an extremely rare mineral that's known from an old cobalt mine that's Carroll County, Maryland. So you don't have to go far to find that if you can spot it with a magnifying glass.
The gentleman with the beard who had a question there.
Oh, no, I just wanted to make a comment. If you define life as non-trivial self-replication, there is something called a cellular automaton which is capable of that, which is an abstract mathematical pattern with no physical substance whatsoever, which was created by an amateur enthusiast of something called appropriately the game of life. So life, there is certainly a possibility for life as we do not know it.
Yes. And this is, I've been fortunate enough to be part of several symposia, conferences, and workshops that discuss exactly these points. And I think that the ultimate result of these conferences is that another false dichotomy, boy, they pop up everywhere in science, is life and non-life. That just simply doesn't characterize the richness of interesting states of information, of matter, of photons, of electrons, of spin states that can exist in nature. Some of those seem to have these properties of self-replication. Some of them have the properties of evolution, of adapting to their environment. Are they all alive? Are they all dead? No, you can't say that. There's a taxonomy that we just simply don't have enough data yet to define. So for simplicity, we define a false dichotomy of living, dead, and then we go about our happy ways because that makes us feel like we've solved that. But beware of any time when you have this or that in the natural world, almost always there'll be some kind of continuum and complexity and richness that is not so easily defined. And I really take your point that there's some people that strongly advocate that these automatons have some characteristics that take them beyond a non-living state, but most of us wouldn't exactly say that they were alive in the sense that those of us who are here today would think of it. So what is that? It's just a richness of nature that we haven't yet confronted and defined and developed the correct taxonomy.
Last question.
My name is Ari Van Tool. I'm not a member. Basically, the elements required for Earth life, you're saying, are so pervasive. And scientists, a lot of scientists seem to expect to find life on an exoplanet. So I'm just wondering, what do they expect the chemical signature to be?
I think those of us who expect that if we're looking for life similar to what we're familiar with, that is, creatures that can move and can evolve, that reproduce, that have some kind of need for energy, need for material atoms that go through those sorts of things that we think of as life form, that carbon is the only game in town and carbon-based molecules are going to be the key. And what's intriguing about this is you might think that life would give you a diversity of molecules that you wouldn't have otherwise, and it's just the opposite is true. When you do prebiotic chemical experiments, you make tens of thousands, hundreds of thousands, some cases millions of different small organic molecules. And if you look at the catalog of all these organic molecules, there are millions of them. I think it's 7 or 8 million in what's called Bilstein now. So it's a vast number. When you look at living things, the inventory of molecules is condensed, compressed incredibly. E. coli uses only about 500 different small molecules. And they're highly idiosyncratic. Only left-handed amino acids, only right-handed sugars, as opposed to the mixture that you find in any abiotic sense. So I think what we're going to look for, if we're actually going to find biosignatures that are based on molecules, they're going to be an idiosyncratic concentration of molecules, perhaps chiral molecules, handed molecules, perhaps just certain amino acids and not others that you might expect. That's the kind of thing I would look for, and certainly that's what characterizes life on Earth.
So I think you should close with your Valentine's Day story.
Why? Oh.
If you think that
yes,
minerals
I
are
will
dry,
I will tell you. This is last week we had published an article which described these rare minerals and talked about a taxonomy of mineral rarity, pointing out the fact, which I think is unknown to almost everybody, that more than half of the mineral species are extremely rare. And furthermore, those rare minerals are present in tiny, tiny volumetric amounts. There's some minerals that are so rare that only one single microscopic grain is known from the entire planet. So we made a press release on this, issued it 4 days before Valentine's Day, and basically said if you want to give your love something really rare, don't give them a diamond because there are billions of diamonds. There's diamonds everywhere. There's vast quantities. De Beers hoards them to make them rarer than they really are. What's really rare are Sardinian ichneuseites. And this went viral. And it bumped gravity waves off the top. We were the #1 science story for 3 days, knocked gravity waves off the top, and we still are one of the top-rated sites for like a week later because people picked up on this. I guess just the whole concept that diamonds aren't that rare, but ichneusite and nevadaite and I mean, it was funny. We just had a laugh. Look just at major news outlets all over the world. 68 countries, 20 languages, 700. It was just insane. It just goes to show you what people want to read. I guess gravity waves just are a little too arcane.
Well, thank you, Bob.
Thank you. My pleasure.
And an appreciation for giving this wonderful talk. I'd like to present you with a framed copy of the announcement of your lecture, signed by the members of the General Committee on behalf of the membership of the Society. So thank you very much.
Thank you, Larry. Thank you all.
So just a few closing announcements before we adjourn to the social hour. As many of you know, PSW depends on you, an enthusiastic, active, and capable membership. And without you, there's not going to be any PSW. There won't be any free lectures. Really, truly. So please join if you're not a member. And if you are a member, please get involved in helping carry out PSW activities. You can apply for membership on the PSW website at www.pswscience.org. It's easy. You go to the website, you hit the membership tab, you fill out the form, and you pay your dues. How many of you are here from Meetup? One. Okay. Well, you're a member. A few. Anyway, if you're a Meetup member, please keep in mind that being a Meetup member does not make you a member of PSW. Please consider becoming a PSW member and contributing to the organization so that we continue to provide free and open public lectures of the sort that you've enjoyed tonight. Please see Membership Chair James Heelan or our corresponding Secretary Robin Taylor if you have any questions about membership, contributions, or getting involved. PSW is a nonprofit educational organization tax exempt under Section 501c3 of the Internal Revenue Code, and tax contributions are tax deductible. Our next lecture, number 2359, will be on March 4th, 2016, and the speaker will be Carol Matouche, Matthew Professor of Art History Emerita in the Department of History and Art History at George Mason University. Our talk will be on From Fragments to Classical Forms, Reconstructing Greek Bronzes and the Ancient Mediterranean Trade in Art. Now, there is currently at the National Gallery of Art an extraordinary exhibit of bronzes that correspond to the subject matter of this lecture. And if you have the slightest interest in Greek and Roman art, I suggest that you go see this exhibit. It's probably a once-in-a-lifetime opportunity. Many of the best reconstructed bronzes are on exhibit. They are extraordinarily expressive works of art. Interestingly, most of the bronzes have disappeared because of corrosion in water. So, although these bronzes were manufactured in large numbers and traded throughout the Mediterranean, we have very few of them. And that's led to the perception that these are individual one-off works of art when in fact they were produced in fairly large numbers. And one of the subjects of the talk will address that issue. So I promise you it will be a very interesting talk, and you really should go see this exhibit. Other lectures in the spring series will be are posted to the website, and the Henry lecture should be posted pretty soon. If you have any questions, please ask me, and we will now adjourn the meeting to the social hour, which will end promptly at 10:30. But fear not, if you want to stay later, some of us will repair across the street to what used to be known as the Jockey Club and is now known as the Fairfax Hotel Lounge to continue the discussion. If you want to join us and you haven't done so before, please talk to Robin Taylor or Lloyd Mitchell or myself, and we'll be happy to show you the way. With that, will the meeting be adjourned? Second? All members in favor? Anybody opposed? Meeting is adjourned to the social hour.